Alright, welcome back to section 6.4, vectors and dot products. In this video, we'll be covering just example number 5 in your notes. You'll learn how to write vectors as the sum of two vector components. So far, you've only studied two vector operations. For the first one, you learned if you have vector u as for 3, you can multiply vector u by some scalar and get the vector 8, 6. So you're just retaining the same direction, but increasing by a magnitude of 2. Number 2, you've also added and subtracted vectors. So for example, if you have, vectors w sub 1 as for 0, and w sub 2 as 0, 3, you can say that the resultant vector u is equal to w sub 1 plus w sub 2, or algebraically, 4, 0 plus 0, 3 comes out to 4, 3. And of course we can see this graphically. Here's w sub 1, 0, 4. Here's w sub 2, 0, 3. So if we go tip to tail, moving vector w sub 2, we see that vector u is the resultant vector of w sub 1 plus w sub 2. Now a couple of things that we should notice here. W sub 1 is perpendicular to w sub 2. And we can check that by taking the dot product. So if we dot them together, multiply the horizontal components and get 0. Multiply the vertical components and get 0, so they must be 0. So with this in mind, I want to say that w sub 1 is the horizontal component of vector u, whereas w sub 2 is the vertical component of vector u. Last thing we should mention before we move on is that the horizontal component will always be perpendicular to a vertical component. So today we're going to go backwards. So given a vector, we're going to find its horizontal and vertical components. So let's start with vector u as being 3. So the easiest way to break it down is to let part of the x-axis be the horizontal component. So let's add a little sun into this picture so it's over the terminal point of vector u. So assuming it's straight overhead. Now the vertical component sketched in, and the horizontal component sketched in as well. So remember that the horizontal will always be perpendicular to the vertical. So let's call the horizontal component w sub 1 and the vertical component w sub 2. So we see that w sub 1 plus w sub 2 is equal to vector u. Now, we in theory didn't know what w sub 1 was before we started. We just said that the ground is part of the positive x-axis. Now, the easiest way to represent the positive x-axis is by the vector 1, 0. And because we didn't know how long this vector w sub 1 should be, let's say that w sub 1 is equal to some scalar c times 1, 0. So if c is bigger than 1, it'll stretch it out. If c is less than 1, like a fraction, it would compress it. So this vector is what we're casting a shadow or projecting vector u onto. It represents the ground. Alright, so now some notation. Alright, since w sub 1 is equal to c times some vector 1, 0, and we didn't know what c was, let's say that, for shorthand, w sub 1 is equal to some vector, let's just call it v. So by the transitive property, we can say that vector v is equal to c times this vector 1, 0. Formally, we say that this projection of vector u onto v, remember v represents the ground, is equal to w sub 1. And that's a big key point right there. We'll highlight that. We said vector u is equal to w sub 1 plus w sub 2. So substituting this in, we can say that vector u is equal to the projection of u onto vector v plus w sub 2. Or, if we solve for w2, so subtract projection of u onto v from both sides, we get w sub 2 is equal to the vector u minus the projection of u onto v. Now luckily we have a formula to do this. So we can say that w sub 1 is equal to, of course, the projection of u onto v. So is the same thing as the u times v all over the magnitude of v squared times vector v. Now, thinking about that, this numerator, anytime we take a dot product, is going to be a number. This magnitude is also going to be a number. So a number divided by a number means that this whole term is just going to be some number, a scalar, times vector v. So we're saying, how much should we stretch or compress vector v in order to make it a perfect fit? So let's back up for just a second and recap what we talked about here. So we said we got vector u, 4, 3. We know that we want to break it down into its horizontal and vertical components. So w sub 1 was its horizontal and w sub 2 was its vertical. And we agreed that w sub 1 plus w sub 2 is equal to the resultant vector u. We didn't know in theory how long w sub 1 should be, so we just needed it to be along the positive x-axis. So that's where we had 1 sub 0. Again, because we didn't know how long w sub 1 should be, we said, let's take 1 comma 0 and either stretch it or compress it to make it fit. So we used a little bit of notation, swapping out w sub 1 with v. They mean the same thing. So this ground, this projection of u onto v, is what we refer to as w sub 1. Now we knew that at this point, vector u is equal to w1 plus w2. And we swapped out w sub 1 with the projection of u onto v. And now we can apply this formula. W sub 1 is equal to the projection of u on v using this formula. So let's take a look at some examples. So suppose 4, 3 is projected onto 4, 0. We can say that the projection of u onto v is equal to u dot v all over the magnitude of v times vector v itself. So u dot v, so some side work, u dot v is equal to, multiply the horizontal and get 16, add it to the product of the vertical and get 16. Other thing we should find is the magnitude of v. Well, the magnitude of v would just be 4, so the magnitude of v squared would be 16. So plugging in numbers, u dot v we said was 16, all over the magnitude of v squared, times vector v is 4, 0. So I see the projection of u onto v is equal to 1 times the vector 4, 0, or simply 4, 0. And that makes sense. So here's vector u. We've got our sun shining down brightly over the terminal point. Its shadow is going to fall perfectly along this vector 4, 0. Now remember, we know that w1 plus w sub 2, its horizontal and its vertical components, is equal to vector u. So if we solve for vector w sub 2, which is the vertical component, we get vector u minus w sub 1, or vector u minus the projection of u onto v. Vector u was 4, 3. The projection we just found was 4, 0. So I can say that w sub 2 must be 0, 3. And that makes sense because in the beginning we said w sub 1 must be perpendicular to w sub 2. So we can use the dot product to verify that they are indeed perpendicular. Dot it with w sub 2. So the product of the horizontal is 0. Add the product of the vertical, 0. Looks great. All right, slightly different scenarios. Suppose vector u, still 4, 3, is projected onto 1, 0. So our vector u is the same, but we're projecting it onto a smaller piece of ground. So in our previous case, we were projecting vector u, dropping a perpendicular onto a vector that was perfect size for it. Now in this case, we're projecting vector u onto a vector that's clearly too small. Luckily, everything takes care of itself, so let's see what this looks like. So projection of u onto v is equal to u dot v all over the magnitude of v squared times vector v. So u dot v again, a little bit of scratch work. Let's see, comes out to 4 plus 0. So u dot v is 4. The other thing we need is the magnitude of vector v. Well, the magnitude of v is just 1, so the magnitude of v squared, well, 1 squared is 1. So let's plug in some numbers and see what happens here. So u dot v is 4 all over 1. Vector v is 1, 0. So this projection of u onto v is simply the vector 4, 0. And again, because w sub 1 plus w sub 2 equals the resultant vector, where w sub 1 is exactly the same thing as projection of u onto v, plus w sub 2, we can then solve for w sub 2. So vector u minus the projection of u onto v. Plugging in numbers, so u was 4, 3, minus the projection 4, 0. We get w sub 2 as being 0, 3. So in this case, we were projecting vector u onto a vector that was too small. The formula takes care of it by extending vector v into the correct length. And the same argument would hold true if we were projecting vector u onto a vector that was much too long. It will be scaled back so it's a perfect fit. Now, before we go on to example 5, let's take a look at one more example. Up until now, we've always been projecting a vector u onto the positive x-axis. That's not always the case. So suppose again that we've got vector u as being 4, 3, and it's being projected onto vector v. So now, instead of having vector v being somewhere along the positive x-axis, which like what we're familiar with, now the ground is actually, well, think of it as a hill, so 6, 2. So again, I'm going to start by drawing in a sun right over the terminal point of vector. So again, this green represents the ground. So its horizontal component is going to be along the ground, and its vertical component is going to form a right angle. So here's my w sub 1, and here's my w sub 2. So our task is first to find out what w sub 1 is, and then solve for w sub 2. So let's do that now. So the projection of u onto v is equal to u dot v, so a number, all divided by the magnitude of v squared times vector v. So a little bit of scratch work. Let's see, u dot v is equal to 24 plus 6. So u dot v comes out to 30. The magnitude of v is equal to, let's see, 6 squared plus 2 squared. So I see the magnitude of v comes out to the square root of 40. So if I need the magnitude squared, it must come out 40. So plugging in numbers, we get, let's see, u dot v was 30 all over 40 times vector v, 6, 2. Let's knock off some zeros here. So we've got 3 over 4 times this vector 6, 2. Distributing it in, we get, let's see, 9 over 2, comma, 3 over 2. So the projection of u onto v is given as such. Does this make sense? So we're saying the ground, this projection, should be 4.5, comma 1.5. Well, that looks about right. Once we still know that w sub 1 plus w sub 2 is equal to the resultant vector. Well, w sub 1, again, is projection of u onto v, plus w sub 2 is equal to u. Solving for w2, we get vector u minus the projection of u onto v. Plugging in numbers, vector u was still 4, 3, minus the projection was 9 over 2, comma, 3 over 2. So subtracting, we get, let's see, 4 minus 9 over 2, comma, 3 minus 3 over 2. Let's see, 4 minus 4.5 is negative 1/2. 3 minus 1.5 is 1.5, or 3 over 2. Now, quick check here. Is w sub 1 really perpendicular to w sub 2? Well, w sub 1 is 9 over 2, comma 3 over 2. Let's dot it with negative 1/2, 3 over 2. Let's see, multiplying these together. In my numerator, get negative 9 over 4, plus, multiply the numerators, 9 over 4, I get 0. So the dot product is 0, so they must be perpendicular. But that vector, w sub 2, is not in standard position. If I moved it, this little line, so it was in standard position, I see that, yeah, I should go over negative 1/2 and then up 1.5. All right, so example 5, finally. Let's find the projection of u onto v. And write u as a sum of two orthogonal vectors, so perpendicular vectors, one of which is projection of u onto v. Well, we got this. So vector u is given by 3, negative 5. And vector v, which we'll represent as the ground, is 6, 2. Okay, let's get those labeled as well. Now this is a little bit mind-boggling. Remember, vector v is your ground, and we start with these projection problems by actually putting a sun, if you will, over the terminal point of vector u. So it actually might help to turn your head a little bit for a moment. So it might help to actually rotate your paper just for a moment. So the sun is in the sky, and we can drop a perpendicular, our vertical piece, onto the ground. So this is w sub 2, and w sub 1 is on the ground. So a little cattywampus, but same idea still holds. Let's spin it back. All right, so now we can apply the exact same process. Projection of u onto v is equal to u dot v all over the magnitude of v squared times vector v. So a little bit of a scratch over here. So u dot v is equal to 18 plus negative 10. So u dot v looks like it comes out to 8. So the magnitude of v is equal to the square root of 6 squared plus 2 squared, or the magnitude of v squared is equal to, it's like 40. So plugging in some numbers, we've got 8 over 40 times vector v, 6, 2. So let's reduce 8 over 40, divide by 8 in the numerator, get 1, divide by 8 in the numerator, get 5. So distributing, we get, let's see, 6 over 5, comma 2 over 5. So this projection of u onto v is given as such. Again, we know that vector u is equal to w sub 1 plus w sub 2. And this projection of u onto v is also known as w sub 1. So vector u is equal to projection of u onto v plus w2, or w2 is equal to vector u minus projection of u onto v. So plugging in vectors, w sub 2, so vector u is 3, negative 5, minus this projection of 6 over 5, 2 over 5. So let's subtract the horizontal pieces, 3 minus 6 over 5. Subtract the vertical pieces, negative 5 minus 2 over 5. Let's see, common denominator, we have, let's see, 15 over 5 minus 6 over 5, comma, let's put this over 1, so minus 25 over 5 minus 2 over 5. Let's see, common denominator now, let's see, 15 minus 6 is 9. 25 minus 2 is negative 27 all over 5. So w sub 2 is given as such. So does this check? First, are they perpendicular? So let's check their dot product. We want it to be 0. So here we get like 54 over 25 plus negative 54 over 25. So yes, that checks. All right, we should also check that vector u really is the sum of vector w sub 1 plus vector w sub 2. So w sub 1, we said was 6/5, comma 2/5, and w sub 2 was 9/5, comma negative 27/5. Adding the horizontal pieces, they have a common denominator, so we get 15 over 5. Add the vertical pieces. Let's see, 2 minus 27 is negative 25 over 5. Let's see, divide by 5, get 1, divide by 5, get 3. So we get the vector 3. Divide by 5, get 1, divide by 5, get 5, minus 5. So yeah, our answer checks. All right, go ahead and try exercise 57 in your notes. Make sure you find w sub 1 is equal to something. Remember, that's the projection of u onto v. And then solve for w sub 2. Check two things. Is w1 really perpendicular to w sub 2? Check number 2. Is u really the sum of vector w sub 1 plus vector w sub 2? All right, go ahead and try the wrap-up for example 5 in your notes. I see that vector u is negative 6, negative 4. The ground, v, is negative 4, positive 3. So I would start by drawing your sun in over the terminal point. You might want to rotate your paper so that when you drop a perpendicular from your terminal point, it's easier to see that this vertical piece, w sub 2, is perpendicular to w sub 1. Come to class with questions. I'll see you tomorrow.